I'm Wayne Pekarsky, and I'm a developer advocate here at Google.
I'm Dave Smith. I'm also a developer advocate here at Google.
And so today, we're going to be talking about how to make your own custom Android things boards. So we showed you during previous talks, if you may have seen them or not, how it's possible that you can create your own custom hardware designs, and you can start from a simple prototype, but you can then take it into a full production device that you could then sell commercially. So let's get started talking about that. So in the sandbox area, you may have seen this little candle demo that we've got set up there. If you haven't been to the sandbox area, definitely go and check that out. But it's an example of a little LED candle that Dave built. And so basically, you've got a little Android thing SOM on there, and it flickers the lights, and that's a little candle. So he built a plastic housing for it. You can put it inside of it. It looks really cool. So you can go check that out in the sandbox. But it's a project that Dave started working on recently, and it's something that he built from scratch, because Dave's a talented electronic engineer, and I just pretend to be one on a day-to-day basis. But the thing I like about it is it's a really compelling example of how to make something really simple that fits within the development model of Android things. And so you can think of it as kind of a hello world example for Android things, a basic setup that does something very simple that you can then expand and do more with later on. And it turns out that building something like this is actually reasonably possible for a hobbyist developer at home using a set of simple tools. You don't need a factory or anything crazy to build something like this. And everything we're showing you in this talk, we're going to show you all the steps, but everything's open source. And later on, Dave will show you the links of where you can go to find the information about how to get it. But everything's open source, so you can modify it, you can study it. And we wanted to show you how this works a bit, because hardware design is one of those things that I've always found is kind of shrouded in mystery. And so for software developers, a lot of people think, oh, wow, hardware is really hard and it's really scary. And I've always thought that too. And it's actually not an imagined problem. It's actually based on real things. It's really complicated to build high-speed electronics. If you look at a modern motherboard or circuit board, there's tons of these really fine-pitched tracks. You can see on this schematic on the screen here a bit of an example. And there's a lot of dense packaging, there's impedance matching requirements, and there's noise and interference considerations. And these are all things you have to deal with when you're building a circuit that runs at very high speed. Now, if you're building just an LED and a battery, that's pretty simple. That's not high speed. But when you're building something that's vibrating at a gigahertz or some frequency, you really need to start thinking about these issues. And one of the interesting things Dave's pointed out to me when we started this talk was if you look at the bottom right underneath that semiconductor chip there are these traces that are like wiggling around. Now, that's not an accident. A very smart, intelligent design person looked at that and went, we need to match impedances and deal with the speed of light of an electron traveling along a wire. And they did that on purpose. But I didn't know you had to even do that. And so if I made that board without that, it wouldn't have worked. So this stuff's really tricky. But it turns out, though, that with the way we do Android things, we can solve a lot of those problems and make them easy for us developers to play with.
Thanks, Wayne. So as Wayne mentioned, one of the things that's sort of a core philosophy of ours when it comes to enabling developers to help build hardware using Android things is this idea of a system-on-module or a SOM-based architecture. And we really think of this as one of the keys to developer success in terms of building hardware. And it has a lot to do with what Wayne just mentioned. So let me kind of walk you through this idea, give you some examples here. So if you were to look at a typical developer kit that you would buy for Android things, it might look something like this. And what you may or may not notice just looking at this is actually two different boards stuck together. So if I explode those out a little bit, what you can see is that we actually have this larger base board, or what we often refer to as a carrier board, and then the smaller module sitting on top. And that's what we refer to as a system on module, a SOM, or a compute module. And that module has all of the compute, the connectivity, and the storage hardware that is essentially everything that's required to build a specific tiny little computer. And that's where all the hard stuff lives from an electronics perspective. That's where all the high-speed stuff is, all those impedance requirements that Wayne just mentioned. All of those things live on that little module. And the only piece that you're responsible for as a developer building a new product is to essentially design your own version of the baseboard that applies whatever is specific to your application. So you might just have a handful of little I/O pieces, maybe some connectors for power. The reason that the baseboard designed with the developer kit is so large is because it has all the possible I/O that could ever come off of this chip expanded out so that it's easy for you to work with. You can connect pieces where you need them. But when you go into production with your design, you can make this much, much smaller and much more compact based on just the elements that you need to apply for your specific application. Okay. One of the other really big things that people don't always think about when it comes to working with SOMs is this idea that if you're going to build an electronic product, something you're actually going to sell to consumers, you have to actually get that thing tested for safety testing, regulatory testing. These are things that if you just develop software, you don't maybe necessarily have ever thought about. And this can cost a lot of money, and it can waste your company a lot of time. You know, certification testing for FCC and UL, things like that, these can cost on the order of tens of thousands of dollars or more. And one of the issues that SOMs solve for you is this idea that these are pre-certified components according to all of those regulatory standards. So the components are FCC certified for all of the wireless interfaces. The power supplies and all of the other things are safety tested through CSA and UL and whatever is required in your specific country. And that drastically reduces, if not completely eliminates, the requirements for testing on your final product. Okay, so it's a huge cost saver to use these pre-certified components in your design. All right, a couple other benefits of using a SOM. One is that at least with the SOMs that we work with, there are a number of them that are actually fairly interchangeable. And this significantly reduces the amount of rework that you might have to do in your design if you decide to move to a different platform or a different vendor. So a couple examples of this. First of all, some of our SOMs, for instance, the Intel Edison, as well as both variants of the NXP Pico that we support, are actually pin compatible, meaning that you can literally take one off, install the other one on in its place, and it will work exactly the same. You don't have to make any changes to your baseboard hardware or your custom design. So if you decide for whatever reason that you need to move from the Edison to the NXP or back and forth, you don't have to make any changes to your hardware to do that. In some other cases, we also provide variants from different vendors so that you can solve supply chain issues if you run into them. So another example is that Pico board that I mentioned uses the NXP IMX6 chip. And we have another SOM that uses the exact same chip called the Argon. So you can, again, target a specific hardware platform, but if you're having supply chain problems getting that specific module, you can just go use the other one in its place. Okay, so it helps you reduce the amount of rework you might have in your design based on having to deal with some of these vendor-based issues. In addition, SOMs are highly available components. These are essentially commodity components that you can buy in single quantity or a handful at a time or in very large quantity for production. You're essentially leveraging the economies of scale that the vendors are participating in on your behalf. So to give you an example, if you were to go directly to a chip vendor and you were to buy the CPUs yourself, buy the memory and all these things to build this onto your specific board, generally speaking, you would have to buy those components in very large quantities, 5,000, 10,000 or more at a time, which is very prohibitively expensive for just doing basic prototyping. What you do with a SOM is essentially the vendors that build the modules absorb that cost for you. They buy 10,000 of the chips and then build the modules and sell them in such a way that you can buy one if you need it for your prototype, or 100 or 1,000 or even more. Okay? And finally, SOMs are well supported, both from Google's perspective, but also with the individual vendors. So all of the vendors that we work with have long-term support contracts in place so that the hardware that you choose to build your product on is guaranteed to be supported on into the future so that you don't have to worry about building something off a design that goes end of life next year. All right, so let's talk a little bit about the tools and processes that you might actually go through to build one of these things. So the first stage generally, and those of you who have played with Android things may have done a little bit of this already, but when you first decide to start using the platform and you want to start building something, you're probably going to purchase one of our supported developer kits. This is an example of one of them using the Intel Edison. And from here, you would generally use that developer kit baseboard to just start prototyping your idea, generate that proof of concept. Right? So you're going to start connecting, in this case, maybe some LEDs, some inputs, a display, whatever you want to do to sort of test out if this thing is actually going to work. And then from there, you can kind of carry it around, show it to the other folks that you work with, say, okay, I think this idea might actually work. And then you can move forward from that process. Now, there's a couple things that you might be using to build these particular designs. One of them is you might use a breadboard, which is essentially just a solderless component that allows you to stick wires in and prototype this thing up however it works for you. But those types of boards are not that portable. Often if you move them from here to here, you lose a connection because the wire comes loose. So generally, what we would typically use in a prototype that you want to actually show to someone else is something called a protoboard, and that's what we have in this example here. And if you want to get up close with this particular piece of hardware, it is in the sandbox along with the final product, so you can look at that design up close and kind of see how it's all put together. But once you've certified that your idea is actually going to work, you're probably going to want to actually build a custom design out of it. This is really cool, and it's fun to post online and see all your friends what you've done, but that's probably not something you can ship in high volume to consumers. So you need to redesign that into more of a custom, compact, integrated system. And so in order to do that, you're going to be using a couple of new tools that you may or may not have ever worked with before. And there's two pieces of content, or what we call hardware design files, that you have to create to build this custom design. The first one is called a schematic and a layout. And we're going to look at both of these so you get an idea of what's inside of these. So a schematic for an electronic product is essentially just a definition of all the components you want to use and how they should be connected together. And this example that we have up here is the exact schematic for that candle sample that you saw pictured earlier. And the first thing that I want you to notice is there's not really a whole lot there. And the reason for that is because all of that complicated hardware that goes along with the CPU and the memory, et cetera, is on the module. So I don't have to add those pieces to my design. All I have to design in are the pieces that are specific to my application. So this design has a connector for the USB, which we use for power, power supply to do some voltage changing from the input to the output, the connector for the actual module, so we don't have to actually lay out all of the pieces that are on that module, just a single connector where we stick it onto our board. And then the I/O pieces, in this case, those little LEDs that we can blink that you saw in the image before. So the schematic is responsible for defining all of the things you want to use and how each of those elements interconnect. And if you've never done this before, there are a number of tools that are really good to get started with this. And I've got them listed there. So Eagle, Altium actually has two products called the Circuit Maker and Circuit Studio, and KiCad. All of these are very approachable electronic design tools that allow you to get started building schematics. One of the benefits of all of these is they're very well supported in the community. So you can get support, you can find tutorials if you're not used to dealing with these. And in addition, all of these have a lot of library support online. So just to give you an example, this entire schematic was built in Eagle, and all of the parts came from open source libraries provided by SparkFun. Okay, so I didn't have to create any of those parts. I just used libraries that already existed. Okay? And that's when you use tools like Eagle, Altium, and KiCad, you'll find good support for doing that. There's actually another reason why these are good tools to choose, and we'll get to that in a minute. All right. So you've built the schematic. This is what I want this electronic thing to do. But now we have to actually define what is it physically going to look like. And that's what the layout is for. So the layout definition is basically you're just drawing a picture of this is what I want the board to actually be. Where do I want the components to be placed? How do I want those wire connections to be routed? And get everything sort of laid out perfectly. Are there any holes that we want to drill in the board so that we can mount it to something easily? All of those pieces are defined by the layout. And this layout is also defined in the same tool. So when you use an electronic design tool like Eagle, you define both the schematic and the layout in the same tool. They're coupled together very tightly, so that when you make a change to the schematic, that can be reflected on the layout and vice versa. Just to give you a picture, if you've never actually looked at one of those layouts before, it might look a little strange. So I put the physical board next to it so you can kind of get an idea of, oh, okay, this is where this connector goes, and these are the holes for the LEDs, they're in the middle, and all of that. So essentially, once you have a schematic defined and then a subsequent layout, this is now something that you could take to a vendor or a manufacturer, and you could have that thing produced. All right, so I want to talk about a couple different definitions because there are two ways that you can go about actually building one of these things. So The first stage that's pretty much always required is you have to fabricate the board. So you talk about, here's someone talking about fabricating a PCB or the fabrication process. That's essentially just building the actual base circuit board. Okay? It's taking that layout, giving it to a vendor, and having them actually etch out all of the pieces on the fiberglass and lay down the copper and all of those things for you so that you have a basis to actually build your product. Then the assembly process is essentially just taking that bare board and installing the components on top of it. And there's a couple ways that this can be done. The reason that we've split these out is because you generally probably don't want to try and fabricate your own PCBs. There are people who do it, and there are tools that you can do to do that. But generally, that's a process best left to a vendor, and it's relatively inexpensive to be able to do this even in low volume. But you might decide, for cost reasons or time reasons or whatever, that it's easier for you to assemble the board yourself. So you might decide to simply buy the components and solder them down by hand or using any other tools that you might have available to you. But you can also have a vendor do this for you as well. So a little bit later on, we'll look at some different options around where you might be able to just get the PCBs fabricated themselves versus having them completely fully assembled and delivered to you with all those pieces in place. All right, so I mentioned schematic and layout before. You could sort of think of these design files as the source code for your hardware. Right? These are the pieces that you develop, and then from there, those can be fed into a number of different tools to generate the content or the files necessary to actually have these pieces manufactured or created. There's a couple other terms that I want you to be familiar with if you're toying around with hardware at all. So the first is Gerbers. A Gerber file is a generated file that is used by CNC manufacturers to actually build your board. It's what takes your layout, turns it into a bunch of CNC instructions, and then a machine goes around and puts drills down and etches out all the pieces on the board and all of that. So it's essentially the generated file that turns into your finished PCB. The BOM and the XYRS files are used in the assembly process. So BOM stands for Bill of Materials, and it's essentially just a list of all the components on your board and the part numbers of those boards so that you can purchase those, and how many of them are on each particular design. Okay. And then the XYRS file basically is an automated file that tells a computer, in this case it's a machine called a pick-and-place machine, how to take those components, pick them up, and drop them on your board. It's the exact location, rotation, and all of that where the component needs to sit so that it can be assembled in the right location. So each of these files are necessary in some cases if you want to fully automate the production process of building the board. However, you could think of these files as sort of your compiled code or your machine code. However, one of the issues with these files is that there's not a lot of pure standards associated with each of these. So there are different formats for Gerbers. A BOM could be something as simple as a CSV file, or it could be something way more complicated. And different vendors are going to have different requirements about how you produce those files so that they can import them into their systems. So this turns out not being quite as simple as you might imagine. And so generally speaking, if you're just getting started with this or you just want to do some very quick basic prototyping, I recommend finding vendors that allow you to ignore these files completely. Okay? And there are a number of them out there, and I'm going to show you a few in just a minute. But there are a lot of great PCB and assembly vendors that will accept your design files directly. So the way I'd like to think of it is if you're new to this or you're not very comfortable with it, and you start going around the web looking at different places where you might be able to build a PCB, if they ask you for Gerber files, go look somewhere else. Okay, you'll be able to find someone that can take your design files directly so you don't have to mess with exporting those and making sure they're correct and all of that. You may get there eventually, and you might want to do that at some point, but at least when you're getting started, that's something that you can ignore completely. Because there are a number of great vendors, and I've highlighted a couple of them here, that can take these directly for you. So on the fabrication side, one of the ones that we've used early in prototyping is Oshpark. This is a great vendor, one, because they'll accept your Eagle files, your Altium files, et cetera, directly, so you don't have to deal with all those Gerbers. But they're also very low cost in low volume because they're what we call a shared PCB vendor. And what essentially that means is that when you give them a board to make, they take your design, and they take designs from other customers that were submitted at the same time, and they panel them all up together on one big piece to run through the machine. So they reduce the cost for you because they're actually running your design along with others at the same time. That works really well for prototyping because it means you can get low quantities at low cost. It has some disadvantages in lead time because it generally means you can't get things that quickly because they have to wait for other designs to come along that they can panel up together. So you generally can't get something next day or the day after that with OshPark, but it works really well for making sure your board is actually correct before you go and actually have it fully assembled. You know, one of the common issues with hardware is when you build your design, you might have accidentally crossed a couple of wires. And unfortunately, unlike with software, we can't just delete and recompile that. We have to actually scratch off the trace, jumper a wire, or just throw the boards away and make some new ones. So until you're certain that the schematic you made is correct, it's good to stick with very low-cost vendors like this and hand-assemble the prototypes until you know for sure that what you designed has everything in the right place. On the assembly side, there are a number of vendors that also make this easy that we've worked with in the past. I've got CircuitHub and MacroFab listed up here. CircuitHub is an interesting one. It's essentially like GitHub for hardware. They allow you to upload your design files, and then you can share that design under an open source license. Other people can fork that design, and you can even buy those designs directly from the website. Okay, so they are an assembly vendor as well as a way for you to sort of share designs between folks in the community. And you'll see actually a little bit later, CircuitHub is where we have uploaded this sample for you to be able to see the hardware design files and play around with it. MacroFab is another output vendor that basically also takes your design files. And one of the nice things about MacroFab is they do more than just electronics assembly. So they will assemble your boards, and they're very good at doing that at low cost, at low volume, but they will also assist you in packaging that into a mechanical housing, or whatever your final packaging is, and also can often help you with inventory as well. So these actually can be a really great partner for a startup building hardware, where they will help you sort of manage all of that process along the way in building your designs and maintaining them and actually getting them shipped out to real consumers. All right. So now Wayne's going to talk about what happens when somebody does this for the first time.
And how not to burn your fingers, which I did multiple times. To get your prototypes done, you've got two different steps. You've got the fabrication step, and then you've got soldering the components onto the board. So you might have access to a local company who can actually make the PCBs where you are. So you don't, I mean, the problem with a lot of these companies is that sometimes they're far away, they're on the other side of the country or around the world, and you don't have to wait a week or a couple days to do your shipping. So sometimes you want to do iterative debugging. Now, when we write source code on a computer, we just make a change, type make, and run it again, and it takes like 3 seconds. But with electronics, there is this production iteration that you have to make, which could take days or weeks or whatever. So what we wanted to do is, rather than having the boards assembled by someone else, I wanted to see how hard it would be to actually solder them myself. And so I wanted to take Dave's prototype and try it out to see if I could do it. So I've got some kind of electronics background. I did electronic engineering many, many years ago, but I've only soldered really large boards with through-hole mounts. Those are the ones where the pin goes through the board. You can go in with a huge soldering iron, and you can make all kinds of mistakes, and it doesn't really matter. So I've done stuff like that, but I've never done surface mount before. So I wanted to see how hard it would be, what kind of mistakes I would make, and then I was going to talk to you about how we do it. Now, the most challenging part is the actual SOM connector that connects the baseboard to the little SOM. And so that's the one that's the most challenging, and we're going to talk a bit about how we went about soldering that. So when you look at the SOM connector, it's really small. If you look at these images, those are images that I shot through a microscope, and on the right you can see the microscope I used, but you can't work with this thing with your own eyes. If you actually hold the SOM connector in your hand, it's this tiny little thing, you can barely see the pins, and you're like, how am I ever going to solder this? So I bought a really cheap soldering microscope. They're about $200. And you basically put it up to your eyes, put the board underneath it, and you can then see all of the detail on the board really easily. Now, it's interesting because it's actually pretty surprisingly easy to work with. You would think that your hands and everything are too large to be able to get in there and solder something so fine, but it turns out when you're under the microscope looking through it, your body adjusts to it, and you're actually able to make pretty fine motions without too many problems. Now, what I did find, though, is that you've got to anchor your hand a little bit, so you'll kind of like press one finger against the table. And then when you're under the microscope, I actually occasionally touch the soldering iron onto my finger because everything's so close, you don't realize how close it is, so that was kind of fun. So yeah, a lot of people around me were like wondering why I was screaming from the soldering station. But anyway, so Make sure you don't drink any coffee before you do it either, because that also gives you the jitters too, so that's also a pro tip. But anyway, so I have a basic soldering iron, I have the microscope, and with that, we're going to try to start soldering one of these things. The problem with a regular soldering iron is that it's too large. So under a microscope, on the left, you can see I've got a ballpoint pen, which shows how big a real pen looks like, the kind that you write with. And you can see that the pen is the size of like 5 of the pins on the SOM connector. So the tip of the soldering iron I had was this big, huge chisel tip thing that is designed for, like, I don't know, soldering huge objects. But we needed something really fine. So you can actually buy a tiny 0.1 millimeter soldering iron tip, and you can see that on the right in the image. So that tip is 0.1 millimeter wide, and you can see that it still looks quite big even compared to the pins on there. But it turns out you can actually solder with this. And it's funny, because if you take that soldering tip and not stab yourself, but prick yourself with it, it's really sharp. It feels almost like a needle. And yet this thing under a microscope, it's got this huge round tip, and it's kind of incredible. But anyway, so that's what it looks like. You can see how small everything is relative to the soldering iron. So that's kind of the challenge that we're dealing with under the microscope. So the first thing you need to do is, when you're doing fine soldering like this, you need to make sure that the solder sticks to the board cleanly. So we use what's called flux for that. So most solder has flux built in, but doing very fine connections like this, you need to have extra flux to make sure it works nicely. So you can buy these flux pens, and actually the pen fills up half the microscope when you're using it, because it's huge. But anyway, you paste a bit of flux down on the board, and then you put the SOM connector down on top of it. And you have to maneuver it in with tweezers or your fingers or something like that, and then you've got to hold it in place somehow so you can actually do the soldering operation. So what you do is you basically bring the soldering iron up, like you can see in this picture here. You bring it up to the pin, and then you've got to bring the solder in against the pin at the same time. Now, what you don't want to do is touch the solder directly onto the soldering iron, because what happens is the solder just melts and wicks up the soldering iron and doesn't go onto the board itself. So you need to make sure that you touch the solder onto the pins and keep the tip away, but at the same time, you've got to touch the wire to heat it up and make sure you solder it correctly. So initially, when I started, I had problems getting everything to flow, but then Dave talked to me, and it's like, you've got to really angle everything apart to really avoid the touching. The solder itself is 0.4 millimeters wide. So if you look at the picture, it's actually quite wide compared to everything. So it's possible to sneak it in there. And after doing a bunch of practice runs, I was actually able to make it work. So this picture here shows a work in progress. As I was working across the board, you can see some of the pins in the bottom right are not done yet, and the ones in the top are finished already. So this is a zoomed up version of that same photo. So this is actually the first ever SOM that I've ever soldered. So I was like, I'm going to document this process so that we can talk about it here in this talk. But I did a pretty terrible job on some of them in the top. But this is literally my first ever attempt at soldering pins on a SOM. So Dave was coaching me over Hangouts to tell me some hints as to how things weren't working out. But you can see that in the top leftish, there are some nice pins there. And then the bottom left with some better ones. Now, occasionally you'll notice there are some pins where I blob the solder across them. Now, those are bad pins. If you actually turn the board on with those pins shorted out like that, you'll probably blow it up. So you've got to make sure that if you ever bridge the solder across the pins, that you've got to get in there and use there's this solder braid you can get that sucks solder out. You can use things like that to remove solder if you need to. So anyway, so I had a rough time getting started, but after a while, I was able to do some pretty clean jobs that look quite nice. So you probably shouldn't do this on your very first board that you're ever making, but after one or two, you'll be better at it. So it's actually something you can do. Now, if you look at the board, there's actually a lot of mess around there. The mess is not the solder, it's actually residue from the flux. The flux is this shiny material that's what makes everything look kind of dirty. You can clean it a bit, but we were trying to find Q-tips and other things to get in there and clean it, but everything's so fine, you can't get anything in there to clean it right. So we sort of cleaned it, but the mess that's left over is the basic residue from the flux. So while this is time consuming, and it might take a few hours to do in your own time, it's actually nice because you can reduce your debugging time. You have the ability to take the boards, solder them yourself, get it done, do some testing, and then if you find mistakes, you can then use that ability to make patches. So in the same way that we patch source code, well, you can patch your hardware as well. So Dave mentioned before, you can scratch the tracks away and you can solder wires. Now, it's not fun to do this, but it is possible. And if that saves you a week, then that's something that you can do as well. And I've seen plenty of boards where you see a wire running across it. It's like, why is that there for? And it's like, well, the designer forgot to put something in, like a magic pad or something that did something right. And it's the equivalent of writing code and then leaving one semicolon out, except that semicolon is the one that powers the circuit and doesn't work. So you don't have a compiler that's going to run your circuit to tell you if it's going to work, so you really have to be careful. So yeah, you got to really think about that. So here is a microscope shot of one of the boards that Dave had professionally fabricated. So you can see there that everything looks super clean. Like, you can tell that a machine has just gone and laid these the solder down perfectly. And the way some of these machines work is they actually put a solder paste down on the board, they put the SOM connector on top, and then they put it through a reflow oven that melts the solder and attaches the components. So you end up with a really, really clean join. And when you buy professionally made electronics, it tends to look a lot like that. So my soldering job, obviously you're not going to put that circuit onto the space shuttle and fly that. But in this case here, this is a nice, reliable circuit where everything is nicely soldered, so it's not done by a newbie like me. And then you attach the SOM onto the board and you power it up and the lights start blinking. And then we have that demo in the sandbox. And then you can stand back and bask in the warming glow of the Android bounce interpolator. So the sample Dave put together, it uses the bounce interpolator to make the LEDs flicker, and you can hold your hands in front of it and get that warm, cozy feeling. So it's a nice, simple example, because on the software side, we can do whatever we want with the LEDs, but it's like a hello world in that it does something very basic. It uses basic components like a few LEDs and a few resistors, and now you're on track to building whatever electronics that you want to build. And you can take this, once you're familiar with it, and you can expand on it from there to do something more complicated for your needs. So once you've built that device, you need to just think about the next steps to take it commercial production. So before you can sell a consumer device, you've got to think about, well, how am I going to package this and enclose it? And so you might need to find an industrial designer to make a plastic housing for you. You can use a CNC printing machine to make something, but those housings don't tend to be very strong. So you're probably going to need to have something professionally made for that. You then, when you ship this device to your customers, you're going to need to package it. So you're going to have to come up with a cardboard box for it, maybe some documentation. It needs to have padding inside of it to protect the product during shipment, maybe legal documentation. You've got to get this stuff made and printed, and it's not something you can just knock up on your laser printer. It's got to look nice. And there are industrial design companies that help with these final steps. And then finally, even little things like if you need a power supply or a cable for your device, you might have to include a USB charger or something like that. While they're cheap, they're not free. They still cost a couple dollars, and that adds to the overall cost of the device that you're selling. And then finally, every country has different rules about what devices they allow, certifications, safety requirements, and so forth. And so for every country you ship to, you're going to have to investigate this and find out what those processes are. And so the SOM has had a lot of testing and certification done on that, but the overall packaging and device needs to also be checked as well. So all of these things I've outlined here do cost some money, and it's important that you think about these things before you get started on your next big, crazy startup idea, and make sure you think about what the costs are going to be. And remember that if you've got a fixed cost like $10,000 for design or certification, you need to sell enough units to bury that cost in each one. If you sell 10,000 of something, that adds $1 to the price. But if you're only making 10 of something, then it's going to add $1,000 to the price of every unit. So you need to think about some of those issues. And remember, just one final little point here is that the nice thing about Android Things is we've helped to simplify the software side of things as well. So building an IoT device, while it might seem easy and you can build your own operating system and put it on there, it comes at a price in that you still need to maintain that device and security updates and so forth. So one of the nice things about Android Things is that you have the power of Android. You can use Android Studio, you can hire phone app developers and get them to write code for your device, and they can use the same libraries and tools that they're familiar with. So you don't need to hire someone who's a microcontroller expert who writes assembly language. There's a lot more programmers available to you. Also, the SOMs, we provide updates from Google. We provide security updates for them. We push the updates out to the devices so that you don't need to worry about maintaining all that stuff yourself. And then finally, you get all the power of Android security. So that we have a huge team on the Android team whose job is to scour the internet looking for security problems and patch Linux kernels and patch libraries, and we take care of that for you. So now, if you were going to make the device yourself and do all the software, you would have to have a huge team of security people and everything to make sure that's taken care of. With Android Things, we've really done a lot to help simplify the software side of things a lot as well, so that you can focus on what makes your product good and not have to worry about all the little details of trying to secure a device and pushy updates and things like that.
Okay. So the moral of the story is, if Wayne can do it, you can probably do it too. So just a couple things to finish up here. If you're interested in sort of learning more about the various hardware platforms that Android Things does support, and as we add support for more that will be listed here as well, you can check out the hardware support documentation on the Android dev site. The Candle sample that you see in the sandbox, as we mentioned, is open source. So the source code and the hardware design files themselves are on GitHub. And the design has also been uploaded to Circuit Hub, where you can actually purchase one of them directly if you don't even want to mess with going through this whole process. So you can take a look at those links as well. And also join our IoT developer community on G+, so that you can connect with us. And Wayne and I are both there answering questions and just give us an idea of what cool stuff you're doing so that we can share it with the rest of the community. So we've got a few minutes for questions. So if anybody has any questions, feel free to hop up to the mics. And let's see what we got.
Thank you.
Thank you.